Simple applications of integration. In this module, you will learn about some simple applications of integration. Integration finds application in many fields. It is used to find area between curves, velocity and acceleration, average value of a function, probability, arc length, and surface area. Here, you will learn to find the position and velocity of an object if its acceleration is given. As you may know, integration is the reverse of differentiation. So, starting with the derivative of a function, the original function is found using integration. Consider an example to understand how to find the position and velocity of an object. A train started from city A towards B at 5 p.m. Time t is equal to 0 with a velocity v of t equal to 40t plus 10 km per hour, where t is measured in hours. Find the distance covered by the train at 8 p.m. Now, consider the solution. Velocity v is defined as the rate of change of position or distance with time and is written as ds dt, where s is the distance. The velocity of the train is given as v of t is equal to 40t plus 10. Thus, ds dt is equal to 40t plus 10. Now, to find the distance function s, you need to integrate the derivative function. That is, s is equal to integral of 40t plus 10 dt, which is equal to 20t square plus 10t plus c. The value of c will be calculated using the initial conditions, when time is 0 and the distance covered by the train is also 0. Therefore, at the initial condition, when t and s are both 0, c will also be 0. This implies that s is equal to 20t square plus 10t. The distance covered by the train at 8 p.m. will be the distance covered in 3 hours because it started at 5 p.m. Thus, at t equal to 3, s is equal to 20 times 3 square plus 10 times 3, which is equal to 210 kilometers. Consider another example. After t years, a boy's height increases at a rate of 15 upon square root t centimeters per year. Assume that at t equal to 0, his height is 46 centimeters. Find his height after 9 years. Also find the time in years when his height will be 166 centimeters. Here is the solution. As height h increases with time t, this means that the rate of change in height h with respect to time t is the derivative of h with respect to t. Thus, dh dt is equal to 15 upon square root t. Now, to find the height function h, you need to integrate its derivative function. That is, h is equal to integral of 15 upon square root t dt, which is equal to 30 square root t plus c. The value of c will be calculated using the initial condition. When time is 0, the height is 46 centimeters. This implies that h is equal to 30 square root t plus 46. Now, when t is equal to 9, h will be equal to 30 times 3 plus 46, which is equal to 136 centimeters. So, the height of the boy will be 136 centimeters after 9 years. Now, to calculate the time when height is 166 centimeters, substitute h equal to 166 in the equation, h equal to 30 square root t plus 46. Now, solve this to get t equal to 16 years. Thus, after 16 years, the height of the boy will be 166 centimeters. Now, consider another example. At a particular moment, a man needs to stop his car to avoid a collision with a cow ahead at a distance of 50 meters from the car. Immediately, he applies the brakes to slow down the car at the rate of 10 meters per second square. If the car is moving at a speed of 30 meters per second when the brakes are applied, will it stop before collision? Consider the solution. Let v be the velocity, a be the acceleration of the car, and s be the distance. Now, velocity v is defined as the rate of change of position or distance with time and is written as ds dt, where s is the distance. And acceleration a is the rate of change of velocity with time and is written as dv dt. Now, because the car is slowing down and the direction of movement is considered positive, its acceleration vector will be oriented in a direction opposite to its motion or retardation. That is, acceleration will be negative. Now, the retardation of the car is given as 10 meters per second square. Thus, acceleration A is equal to dv dt is equal to minus 10 meters per second square. So, velocity v is equal to integral of a dt, which is equal to integral of minus 10 dt, which is further equal to minus 10t plus c1. However, when the brakes are applied, then time t is 0 and velocity v is 30 meters per second. On substituting the value of v and t in the equation of velocity and solving it, you get the value of c1 as 30. Therefore, v is equal to minus 10t plus 30. This implies that ds dt is equal to minus 10t plus 30. To find the distance, you will need to integrate the equation of ds dt. So, s is equal to integral of v dt, that is, integral of minus 10t plus 30 whole dt. This will give s as minus 5t square plus 30t plus c2. To determine C2, the stopping distance S is measured from the point when the brakes are applied, so that at t equal to 0, S is also equal to 0. Now, on substituting the value of S and t equal to 0 in the equation of distance, you will get the value of C2 as 0. Thus, distance S is equal to minus 5t square plus 30t. Now, the stopping distance S could be evaluated on knowing the braking time, and the time can be determined from the equation of velocity. Thus, the car stops when V equal to 0. This implies that V is equal to minus 10t plus 30, which further implies that t is equal to 3. When t is equal to 3, you get the distance S equal to minus 5t square plus 30t, which implies that S is equal to 45 meters. Thus, the car stops at a distance of 5 meters from the cow. In this module, you have learnt about some simple applications of integration.